So now that we're starting back up, I want to actually take a step back. I kind of went through a bunch of stuff at the end just because I wanted to end at a thematic unit, right? But I want to take a step back and talk about some of the models that I briefly mentioned. So one thing I mentioned when we talked about emergence was traffic, right? And this is actually a classic example of a traffic jam model. So what's interesting about this model, and I'll just show it off to you, is that the red car, it has nothing special about it, except we chose to highlight it so you can see what one individual car is doing. And every single car has the same rule. It basically accelerates until it reaches a speed limit, right, as fast as it can. But then if there's another car in front of it, it slows down, right? And you'll notice that it accelerates slower than it decelerates. That's what the parameters on the left are controlling, right, is how fast it accelerates and decelerates. And what you'll see is that traffic jams quickly form in this model, even if there's no obstructions. There's no, like, police car pulling someone over, right? There's no log across the road. There's no wandering group of animals crossing the road, right? Like, it still results in traffic jams, right? So why do you think that happens? Any ideas? Any theories as to why a traffic jam comes about? Like, let's be clear about this, right? Like, if I space those cars out appropriately and run this model, right, there's no traffic jam. It just runs. In fact, and I can change the parameters so that it happens every single time, right? But why do we get traffic jams in this particular case? Because the car behind is faster. Yeah, for sure, right? Right. Right. So there's no information transfer, right? So I don't find that out until I get closer. Yeah. Yeah, more number of cars than can possibly fit in the space. If I reduce the number of cars, right? So the nice thing about agent-based modeling is we can test these hypotheses, right? So if I go down to 9 cars, yeah, we get a little bit of a traffic jam at the beginning, but then everyone's happy, right? So yeah, reducing the number of cars helps for sure. I can also, you're talking about like people can't speed up or slow down fast enough. Well, what if I allow people to accelerate faster, right? Then I kind of get a traffic jam, but it doesn't have as much of an effect, right? And now I don't have a traffic jam at all, right? Because if I can accelerate faster, right, then I can move away from any traffic jam I'm in a lot quicker, right, as soon as there's clear road in front of me, right? So what's interesting to me is that the system does not require, like a lot of people, they get in a traffic jam, they're like, oh, what's causing the traffic jam, right? Like, what's going on up there? Well, nothing can be causing the traffic jam, right? The traffic jam could just be a product of normal interactions of the individual cars. And in fact, some clever Japanese scientists did an experiment on this. They actually had people drive a car, they had about 10 cars in a circle. If I can find the video, I'll put it up later. Had 10 people drive a car in and start driving in a circle, just around and around in a circle, at a constant, 50 kilometers an hour, right? They said just keep the speed right at 50 kilometers an hour. That's all they told them, and just drive in a circle. A traffic jam formed within the first 5 minutes of that, right? Even though that's all they told them, right? So people are very bad at kind of exactly applying uniform rules is another thing, right? Each of these, this is the case where they're all doing the same thing, but some people are driving a little faster than 50, some people are driving a little less than 50, all of a sudden a traffic jam forms, right? I also like this model because it's a good representation of this concept of emergence, right? No one car is the traffic jam, right? The traffic jam is a product of multiple cars interacting, right? And in fact, this is related to a problem that a lot of people have when trying to understand complex systems, which we sometimes call level slippage, right? People think of the emergent phenomenon as something that has its own power or actions. But the emergent phenomenon doesn't, right? The traffic jam can't do anything, right? Only the individual cars in the traffic jam can do something. This model was actually developed, by the way, by a fourth grader, so someone who is about 10, right, built this model because when they were interested in traffic jam, working with someone who, not this version of it, but a version similar to it, right? And they were interested in what caused traffic jams. And they built this model thinking that there would be no traffic jams, right? And then they found traffic jams right away. And one of my colleagues took this model and was presenting it to a group of physicists. And he said, he was pointing out, one of the interesting things about it is that the traffic jam itself moves backwards, right? Even though the cars are all moving forward. And one of the physicists raised his hand and said, I've heard about this. This happens on the LA freeway all the time. The traffic jam is moving backwards and the cars are moving forward, so they collide and there's an accident. Well, the problem with that statement is that there is no traffic jam. Like, cars can't collide with a traffic jam. They collide with another car, right? So the fact that the traffic jam is moving backwards has no effect on the collision, right? It's a natural outcome of it. And that's a great example of level slippage, where that particular person, a very smart person, right, had confused the actions of the emergent system with the actions of the individual entity, right? And the emergent system doesn't have its own actions. It only has what emerges out of the individual actions, right? And so a lot of people get confused by complex systems for that. There's a great book by a guy named Mitch Resnick called Ants, Termites, and Traffic Jams, where he talks about these exact phenomena from a cognitive science perspective, right? From how people actually understand these phenomena. And he did a lot of that work with my mentor, Uri Walensky, back at MIT when they were there together as graduate students. Okay. Another one I want to show you. Biology, right? No. I don't know where it is. Earth science. Okay. Okay, so got another quiz for you. So, we've got a forest. This is a forest. You have to use your imagination. You're looking down on it, right? On the left side, you'll see there's a long red line, right? That red line is a fire that has started in the forest, right? Now, the way the fire works in this forest is if the red line is touching a green dot, the green dot becomes red, it catches on fire, and the red line becomes black, it's burned out, right? And so the simple question I have for you is, will the forest fire get from the left side of the screen to the right side of the screen? Does that make sense? That's the question. So how many people, raise your hands, how many people think the forest fire, and let me point out one other thing. The density is 57%. What we mean by that is with a random probability, actually it's not random, it's deterministic. So 57% of the screen is covered by green spots, right? And 43% is covered by black spots right now, right? So more than half of the forest is actual forest. It's actually trees, right? So given those numbers, how many people think that the red line will get from the left side all the way to the right side? If you think so, raise your hand. Some people. How many people think it definitely will not get all the way to the right side? A couple more, maybe. You guys got some even splits. Okay. Well, nice thing about agent-based models is we can just set it up and run it and see what happens. Okay. So it's going along, it's chugging along. That one's kind of keep going, and it stops. In fact, only 14% of the forest actually burned, right? Let's try it again. Maybe that was just a random coincidence where it didn't happen. Now, let me be clear. There is every reason to believe that if you were to align the trees directly across the middle, it would immediately go from left to right, right? Because 57% is way more than it takes to actually get across the middle of the forest, right? So there's something about this particular number that seems to not work very well, right? And if I lower the number, obviously it works even less. Now, everyone pretty convinced it's not going to reach the right side of the screen, at least not on a random probability. So I'm going to move that up to 62%. Not very much higher, right? 5% more trees. So a little more dense, but not that much. Now, how many people think that the fire will get from the far left to the far right edge of the screen? How many people think it won't get from the far left to the far right? Okay. Well, let's run it and find out. So I think that was closer to an even break, maybe. Or actually, I think more people said it won't, but... So there you go. It's already well past those percent burn that we saw the last time. And there it goes. It got to the right edge of the screen, right? And in fact, wound up at 89.6% burned, right? If I run it again, maybe it's just a fluke. Let's run it again. And again, as you can see, it's well past that 12, 13%. It's now at 75, and it's now touched the right side of the screen, 87.3%, right? So this is a classic example of a phase transition, right? Sometimes called a tipping point, right? Maybe a leverage point, depending upon how you think about it, right? Yeah. Yep. Yep. So you're absolutely correct, right? This is a idealized simulation, right? This is a model, remember? And models will background certain elements and foreground other elements. And right now, this model is really foregrounding the idea that depending upon the density of the forest, that has a big effect. But we don't look at all at things like how dry the forest is, how wet the forest is. We don't look at sparks, right? What if a spark flew across a gap, right, with a certain probability? None of that's taken into account. There's no wind, right? There's no wind affecting this model whatsoever, right? So there's a lot of things we could add to this model. And in fact, in our book, we go through like 3 extensions to this model that you could do to make it go to change up the model and make it more realistic. It all depends on what you're trying to prove. I'm only trying to prove that tipping points exist, right? So I don't really need to actually get a real model of a forest, right? But people like the Redfish group, they actually have a product called SimTable, and SimTable is actually used by forest managers trying to simulate forest fire spread. And they will go in there and they can manipulate the SimTable and kind of look to see, like, what if we cut a bunch of trees out in the middle, right? Will that stop the forest fire spread? Like, how can we control the forest fire spread? So they could stop at a certain point? Yeah. We could do that. Actually, we can do that pretty quickly. I'll do it. Why not? Well, I'll show you how to do this really quickly. So this will be the first time you've seen the NetLogo code. It's pretty easy to manipulate. Let me blow it up. So if you look at it right now, it says ask patches with px score equals min px score, which basically says ask the patches, and patches are the squares. They're the background of the NetLogo world. We'll get into this a little bit. If their x-coordinate is the minimum x-coordinate, then set them on fire, right? But what I could do is I could start the fire someplace else instead. So I could say, let me comment this one out, put a new one in. Ask n of, say, 100 patches. Will that work? Yep, that should work. Okay. So you can't see it very well because the patches are so small, but there's 100 red dots in that fire, right, the forest right now, right? If I started running, right, it comes out of those 100 red dots, right? And of course, if I do it that way, rather than starting them all on one side, right, I get a lot more of the forest burned. It's still not as much, right? But I get a much different result out of it. So it's very easy to manipulate these kind of things in agent-based models, right? And we'll get into that more as we go through this course. So what was that? Slums areas, is that? Yeah. Yep. Is more likely to start in those locations? Yeah. So you could look at that. In fact, actually, interestingly enough, like I don't want to get into too many details here, but you all probably saw the burning of Notre Dame, right, on the web, right? What's interesting about that is that neighborhood is very dense, right? It's extremely dense, that island that it's on, but nothing burned besides Notre Dame, right? And the reason why was because it actually was meant to burn the way it did. It was meant that the roof would burn and the stone walls would protect the rest of the neighborhood, right? And so it basically, so you could do a bunch of other things, right? You could look at slums, you could look at places where they're built on top of each other and they could burn very quickly. Or you could look at building with like stone, but in a dense neighborhood and seeing what would happen there, right? And seeing if that would affect things. That's all way beyond the scope of what I'm going to talk about right now with this model, but it's a very interesting idea to think about for sure. So that just shows you how easy it is a lot of times in these agent-based models to change some of the initial conditions. One of the things I want to mention quickly before I move on is that this relationship right here so what you see overall, if you were to run this model many, many times, is from 0 to 57%, there is almost a 0 probability that the fire will go from the left side of the screen to the right side of the screen. From 62 to 100%, there's almost a 100% probability that the fire will get from the left side of the screen to the right side of the screen. So this is clearly a phase transition or a tipping point. And in fact, this model is a general example of what's known as a percolation model that has been well studied in physics and other places. And there's actually ways that you can mathematically prove that this density is the result. So you don't really need the computer simulation, but I think the computer simulation is a lot more compelling than just seeing a bunch of numbers, right? It makes it more obvious to you how this system will actually work. Okay. Let's see. So that one. Oh, one last model. Two last models I'm going to show you. So we mentioned the giant component model. So let me pull up that one. So again, this is one that shows this kind of nonlinearity effect, right? So all this model is doing, at every time step, so we have 80 people hanging out in a circle, right? And every time step, 2 of them decide to talk to each other, right? And it's randomly chosen which of those 2 are, right? And what we're going to draw in red is the group of the largest number of people talking to each other right now. And if there's 2 groups like there are right now that have the same, we'll randomly choose one of them to be the largest, the red group, right? And so we're going to simulate this process over time, and we're going to track that size of that giant component. And what you see, it's not quite linear. There's some jumps in it, but there is a fairly smooth curve up until about this point, right? And now it's going to start heading up quite steeply, right? And the reason why we have that is at that line where that blue line is, the number of connections per node, right? The number of links per node goes over 1, right? Which means that before that point, there were more nodes than there were links in the network. After that point, there are the same number of links as there are nodes. And at that point is when you see this nonlinearity effect occur, right? The more people become connected quickly over time as soon as that network comes in, right? So it's another example of how you can have nonlinear effects in these systems, right? And if I run the model multiple times, you'll see the same results, right? Now, I'm not saying that this model is necessarily representative of any real-world system, but it's one of these things that's useful to know, right? If you're thinking about influencing a network, if you're thinking about spreading ideas, right, you could think about it as I'm trying to influence, that the red people are the people that I've been able to influence. And what this shows you is that you might only be able to influence a few people for a long time, but eventually that's going to spill over, right? Because those people are going to start influencing other people, right? There's going to be a larger and larger spread of those concepts over time. Okay, one last model, then we'll go back to talking. Yeah? Yep, it's essentially creating an Erdős-Rényi type graph, right? If you look at it, this one's a little more, it doesn't have to be this complicated. But this is the essential, this is what happens in each time step. We choose one of the turtles to be node 1, one of the turtles, those are what the nodes are, by the way, we'll get into that discussion later. One of the turtles to be node 2, and we ask the node 1 neighbor if they don't already have a link, create a link. That's all it does, right? And we're just choosing one randomly each time. So it is very Erdős-Rényi in that kind of sense. Okay. Let me show you one. So this is the Schelling model. In the Schelling model, also called the tipping model at times, also called the segregation model, right? We have two different groups of people, and Schelling originally described this as segregated cities in the United States, so white people, white individuals and black individuals, right? And in this case, we have peach kind of people and blue people, right? And if they're square, that means they're happy right now. If they're an X, that means they're unhappy, right? And to be happy, they just need 30% of their friends to be like them, right? And right now, this is just randomly distributed at first. And the average similarity is 50%. Means that on average, for any individual, 50% of their friends are similar to them. Now, let's be clear. If everyone had exactly 50% of their friends like them, everyone would be happy, right? But that's not the case, right? You see a bunch of X's up there, and that's because they're randomly distributed, right? And in fact, 15.1% of them are unhappy. So I'm going to run the model, but before I do, I have a quick question. How should I put this to make it a question that everyone can participate in quickly? How many people think that the percent similar will be higher than 50% after I run the model? Does that make sense? So raise your hands if you think that the percent similar will wind up higher than 50. Oh, I don't know if I told you the rule, did I? Yeah, so let me say what the rule is. So if you're unhappy, you move to a random empty location. That's the only rule. There's no other rule, right? It's a very simple rule. So if you're unhappy, you move to a random other location. That's all there is. If you're happy, you don't move, okay? So how many people think the percent similar will be greater than 50% once I run the model? Percent similar. So how many people are next to other people of the same type? How many people think it'll be greater than 50%? Anyone think, a lot of people, everybody pretty much. How many people think it'll be greater than 60%? Maybe one or two. Now there's some social effects going on there, I see. Okay. That's interesting. I want you to ask, anyone say 70%? Greater than 70%? 1, 2, 3, maybe. Okay. Well, let's see. Let's run it and find out. All right. .3% similarity, right, by the time we're done running. All right. So why does it wind up so segregated, right? We were in a pretty good condition, right? And yet we wind up at this much higher level. Any ideas as to why that happens? Anything you notice about this pattern, right, compared to the original pattern? What was that? Yeah, there's definitely dense clusters, right? All the blues are kind of focused together, all the pinks are focused together. That wasn't the original case, right? They were much more evenly spread, right? So one reason that Schelling argued is what he called the tipping point, right? A tipping phenomenon. So if I'm unhappy, let's take a look at it right now, right? So let's start it up again in the initial condition. Let's find a good one. Let's find a decent one. Let's say I'm this individual who's unhappy, right? Because surrounded by blues with only the two pink ones right there. If I move, right, out of here because I'm unhappy, then this individual now has less people next to it that are similar, right? Which means it might move out of there, right? Because it's going to become unhappy. And so one person leaving kind of a quasi-stable neighborhood can result in a lot of people leaving, right? And this is what some people blame for what they call the white flight scenario that happened in the United States in the 60s, where the inner cities had more and more black residents, and so a couple of people decided to leave, even though a lot of people weren't that racist, right? And as a result, it kind of created this phenomenon that a whole bunch of the white population left the inner city neighborhoods, right? And Schelling wrote this model. It was really interesting. Schelling wrote this model back at that time period. And what he was arguing for, right, was that that you don't really need, people aren't really that racist. He kept seeing these patterns of behavior and claiming, well, people don't really hate each other that much, right? Like, why do we see these patterns? And so his argument was that this, what he called a mild discrimination, right? Like, I kind of want to have a couple of people who look like me near me, right? Was enough to drive a pattern of behavior that seems like it's much more racist than it actually is, right? And he calls the paper that he calls his book, eventually that he writes about this phenomenon, Micro Motives and Macro Behavior, right? And that's very much related to the agent-based modeling idea that there's these individual level rules that give rise to emergent patterns of outcome as a result. By the way, Tom Schelling died about a year or two ago, 2 years ago, I think now. I happened to be one of the last people to interview him, actually, before he passed away. And it was very interesting. It was insightful to me because I asked him, so how did you come up with that? So this paper has won a ton of awards, right? It's been nominated. It wasn't what he was cited for when he won the Nobel Prize. It wasn't what he was cited for when he won it, but it definitely contributed to his overall reason for winning. He actually won the Nobel Prize for his work on negotiations during the Cold War, between the United States and Russia. But nonetheless, this paper definitely fed into that. So I asked him, well, how did you come up with this model? Where did you, were you reading a bunch of psychological theory about how people decide this? He's like, nope. I just talked to all my friends, right, and figured out where do they decide where to live. And they kind of all said something similar to this, where they were like, oh, I want to be near some of the other professors, right? I don't want to have it all be professors, but I want to be, live near a couple other professors, right? And so he decided to take that same model and apply it to this more racial situation instead, right? And he got this interesting result. By the way, I mentioned to you briefly, this model, when it was originally done, was not a computer simulation. His original simulation was done using a paper and pencil and eventually a checkerboard and some coins, some pennies and dimes, right? And he actually literally would pick them up and move them around the system, and he'd write down the results, and then he'd do it again, write down the results, do it again, write down the results. And that's what made up some of the data in his original paper on this subject, right? And so the point is that the agent-based model, there's nothing about a computer that makes an agent-based model an agent-based model. except for the fact that once he had the computer version of this, he could run it a lot faster, right? And run it many, many more times and try it a lot of different circumstances, right? You could imagine how long it would have taken me for, what is this? This is like 2,500 agents. If I was moving 2,500 agents around on a checkerboard up here to demonstrate this to you, right? But the computer simulation really helped him actually get a lot of robustness to his results. And so that's part of the reason why I think we're seeing the growth of agent-based modeling in the last 10 to 20 years, because computer simulations have gotten cheaper. And with computer simulations getting cheaper, that means that by definition, we can use them to solve a lot more problems, right? We can look at a lot more systems. Okay. And I transition back to talking about the theory of agent-based modeling. And one of the things I want to talk about is the idea of representation. And this is something I alluded to at the beginning. I am not a big fan of saying that agent-based modeling will solve every problem, or that data mining will solve every problem, or that a game theory model will solve every problem. I think that you should use whatever modeling approach has the best representation for the system you're looking at. And one of the reasons why agent-based modeling works well is because, for a lot of cases, because its representation is very similar to the real world, right? If I want to represent a human in my model, I write a piece of code for a human, right? If I want to represent the government, I write a piece of code for the government, right? A lot of other modeling simulations, you might say, will be like, well, let's assume that X is the number of influenced people and Y is the number of uninfluenced people. That representation is more strained, right, than a lot of representations you can come up with here. So, yes, right, that flocking model could be written as a series of equations that describe where the birds are and how they interact with it. And in fact, I mentioned people have done that, right? But that representation, in some cases, is not as useful as the representation of the computational model, right? Especially if you want to do something like, for instance, simulate bats flying over Gotham, right? You can't use the math model to do that, but you can use the computational model to do that very easily, right? So representation is very important, and so I want to make sure to express that that's the case, right? A lot of the problems, a lot of the situations that we're going to look at could have been done using a math model, using a statistical model, right? But the agent-based model gives you a different representation that in many cases is easier to understand and more powerful description of the system. In fact, new representations of a system can change the way we view things completely, right? So, for instance, in historically, right, one of the first numerical systems that was of use in commerce worldwide was the Roman numerical system, right? But the Roman numerical system is extremely difficult to use whenever you're trying to do any complex mathematical calculations, right? It's really only useful for counting, and that's about it, right? The Arabic numeral system was very useful, right? And in fact, introduced the notion of zero. There is no notion of zero in the Roman numerical system, right? And so as a result, it became much easier to do much more complex things in it. And so you could solve a wider variety of problems. I would argue in many ways that using agent-based modeling is sometimes equivalent to moving from a Roman numerical system to an Arabic numerical system. It allows a different representation of the world, right? And allows you to change the way you're looking at it, and so therefore you can ask new and different questions. Complex systems, as we mentioned, are composed of many interacting parts. Those parts are often connected in complex ways. Agent-based modeling is one solution to representing complex systems in an easy-to-understand way. And you may have heard this term before, but we think of agent-based modeling as, in fact, a third way of doing science, right? So this comes from a famous paper that Robert Axelrod wrote in 1997, right? There are two traditional ways of doing science. Induction. Induction is the idea that you infer from particular data to a general theory, right? So you have a set of data and you infer a theory from it. Or deduction. Deduction is the idea that you start from a theory of first principles, and you infer a theory of behavior from that, right? In some ways, agent-based modeling is a third way. It's a generative way, right? We're going to use first principles to generate our agent-based model, and then we're going to generate a set of data from those first principles that can now be compared to real-world data that we see, if we want to, right? And so this is a generative approach to doing science. It's different than either the inductive or the deductive approach, right? Moreover, there's this notion of integrative understanding, right? If I know what the first principles are and how they interact to generate the large data sets on the other end, I have a better understanding of how I might manipulate that system to affect those results, right? If all I know is statistical modeling, right, where I take the empirical data and I represent it in a simpler form with like means and standard deviations, that doesn't tell me how to manipulate those results. What if I wanted to change those results to have something different, right? And if I have a game theory model, which says that given these assumptions, right, this will inevitably be my outcome, right? That doesn't necessarily tell me what to do if I want to get a GDP of 10% higher next year, right? Like I can't come up with a numerical answer, right? Generative modeling allows you to do both, right? It allows you to talk from a first principle, talk about what I could change that then will result in a different outcome, right? And in fact, you know, there are some people call these models mechanistic models, right? Because they tell you potentially the mechanism that creates the outcome that you want, right? And I should say there are two ways of approaching this. One is integrative understanding. If you know the first principle of rules, you can figure out the aggregate pattern. And then there's differential understanding. If you know the aggregate pattern and you figure out what inferential rules give rise to them, what individual rules give rise to that, right? So there's two different ways to approach agent-based modeling from the integrated perspective and the differential perspective. So that's what I want to. I'll stop there with what is agent-based modeling, and I'm going to transition now to when to use it. But are there any other questions about that before I move on? Okay. Give me 1 second as I switch slide decks. Okay. So I should say, by the way, I talked a little bit over this. I'm going to switch this afternoon to tutorials, right? But in general, from here on after that, I'm probably going to go back and forth from tutorials to theory and tutorials to theory, and I'll let you know when that's happening. It just makes more sense, given some of the way we're going to build through this material, to sometimes have the tutorials in the morning, right, and stuff like that. So I'll let you know at each time point where we're going with each. This afternoon, it's theory and then tutorials, but you know. And also, if I remember correctly, there are no 5:30 lectures, right, for either of the next 2 days. There is one on Monday, right? So we'll be ending a little bit earlier than you have been ending for the past couple of days, right? Let's jump into when to use agent-based modeling. So in the textbook and in a couple of papers we've written, we propose 6 kind of features to look for when a system might be appropriate for understanding from an agent-based modeling perspective. And you'll notice that a lot of these are actually similar to things that you might notice in a complex system, right? And that's not, someone asked during the break if they're exactly the same, if agent-based modeling is always useful for understanding complex systems. And they're not quite, right? There is some difference between them, but there is a lot of overlap between them as well, right? So when should you use agent-based modeling? And I'm going to talk about 6 properties, and I'll go through each of these in detail. But let me mention them briefly. Medium numbers. You don't want systems that have millions of agents, and you don't want to have systems that have 1 agent, right? You want something in between. And I'll talk about what I mean by that. It actually has nothing to do with the actual quantity. It has more to do with the properties of the system and how parts affect each other. Heterogeneity. If the agents are different from each other, if they have different properties, agent-based modeling is going to be more useful, right, than other approaches. Complex but local interactions. Do the agents take actions based upon global information or based upon local interactions? And can they do things like take different actions based upon their history of interaction with that particular person, right? That's why I call it complex interaction. Rich environments. Are they in a world that's just a flat space, or are they in a world where their environment is really defined by social connections or defined by geography, right? Then agent-based modeling is going to be very useful. These first four things, the more of them you have, the more likely agent-based modeling will be useful, right? The last two, I would call the fifth one, I would say it's almost a necessary condition for agent-based modeling. If there's no temporal system at work, if you're just interested in static fixed points, equilibrium, right? Agent-based modeling is rarely useful, right? Agent-based modeling is really a model of process and not a model of pattern. And so therefore, you have to have a process involved, usually to make agent-based modeling useful. Adaptation is often a sufficient condition for agent-based modeling. And by that I mean that if the agents are actually changing their rules of behavior over time, right? I don't know of any other framework that really allows you to study that very well besides agent-based modeling, right? Most other frameworks, most other modeling approaches I can think of require that the rules of behavior to remain constant once you start the model, right? Agent-based modeling doesn't make that requirement. It's one of the few modeling frameworks that doesn't. And so as a result, I would say that that is usually a good example that if you have that phenomenon, then your model probably does need to be done using agent-based modeling. So the idea of medium numbers actually comes from one of the first papers I read when I started thinking of complex systems as its own field. And this paper was written in 1996 by a guy named John Cassidy. And John Cassidy is not actually a scientist himself, but he's a science journalist, and he's a very smart science journalist who usually embeds himself with a group of scientists for a while and then writes about what they do, right? And he wrote a paper called "Seeing the Light at L for All," that's about the L for All bar problem, which I'll talk about later today. And in this paper, he talked about medium numbers as something that agent-based modeling is useful to understand, and he says it the same way I do. It's not that there's 100 agents, and that makes it a medium number, right? It's that a small group of agents within the system can dramatically alter the outcome of the system. And that can only really happen in these medium number spaces, right? So if I have, 1 billion agents and 5 agents can't really affect the system at all, right? Then that's probably not appropriate for an agent-based modeling approach, right? If that's all the systems are. I'm probably better off, like for instance, modeling the patterns of gas in this room, right? I'm probably better off using something like mean field theory than agent-based modeling, right? If there are too few agents, right, that's also not useful for agent-based modeling because usually I want more richness than agent-based modeling will normally provide me, right? Like if I want to talk about the U.S.-China trade war and how negotiations are happening between them, right? Having an agent for each one and just having it, is probably not going to provide me enough richness compared to providing detailed analysis, right? Detailed kind of ethnographic analysis, and it's not really ethnographic, country graphic analysis of what's going on. That's just, right? The key is that the number of agents that can affect the outcome of the system be a medium number, that be a relatively small fraction of the overall population, right? If that's the case, then we have a medium number of agents. Heterogeneity, right? So in the agent-based modeling framework, agents can be as heterogeneous as they need to be, right? So, and I should say, there was another question that came up during the break, is do all the agents have to have the same rules? No, they can be different, right? So you can have a group of agents who represent, for instance, consumers investing in a bank, and then you can have the bank itself be an agent, right? And it can have different rules and different properties than the consumers. But the consumers themselves can have different properties. Maybe some of them are wealthy, some of them are poor, right? And maybe they make different decisions based upon that, right? So that's all examples of how you can have different heterogeneity within these systems. Even the flocking model, which seems like it's non-heterogeneous, right? Like it's very homogeneous, right? Because all the birds move the exact same way, they all do the exact same thing, actually has heterogeneity in it. Because each of those birds has a unique starting condition, right? They have a unique position in the space, and they have a unique angle. And at any point in time, they have a unique point and a unique angle that they're taking, unique traveling pattern they're taking in the system, right? And that would be very hard to model in a lot of traditional systems, because if we have to keep track of 5,000 bird vectors, right, that's very difficult to keep track of, right? But when you just have 5,000 computational agents and they all store it themselves, it becomes very easy to track these kind of things. So that makes agent-based modeling useful. So agents can model complex interactions. So for instance, in the preferential attachment, the giant component model that I showed you, the agents just form links randomly with each other. But what if I have a model in which some of the agents are into science fiction and some of the agents are into comedies, right? Then maybe they're more likely to form interactions with people who prefer the same kind of movies, right? And so I can model that fairly easily, right? Or maybe one of the people who walks into the room knows that, like, oh, I talked to that guy at the last party and he just would not shut up. I can't talk to him again, right? Those kind of history-dependent decisions can also be built into these models fairly easily, right? By keeping track of the history of the agents' interactions. One of the driving fundamental assumptions of agent-based modeling, though, is that there is no global knowledge. Agents do not automatically get to know the state of the system, right? They infer the state of the system by talking to their local neighbors, but they don't get to know it. And the reason why is because we're trying to keep these models as close to the real world as possible. And in the real world, very rarely do I have instant access to the global state of the system. I might eventually find out, from the election results what happened, right? But on TV, but I don't get to know that from talking to my neighbors ahead of time, right? I don't somehow instantaneously know that everyone's going to vote BJP tomorrow, right? Or something like that, right? I have to infer that from talking to my friends and talking to their neighbors, which is why we often get these dramatic effects in today's world, right? Where, for instance, in the US, I only know like one person who voted for Donald Trump, right? But somehow he became elected president, right? And it's because of the fact that we only get access to our local networks, right? And our local networks are extremely biased given our past preferences and our past behavior, right? I keep forgetting I have a clicker. So the rich environments, right? So the environments the agents interact in can be extremely rich. So we've already seen social networks, right, where we've kind of teamed up. And we've seen a little bit of geographical systems, right? So we've seen agents embedded on real worlds, right, where they're making decisions about the GIS data in there, right? The environment itself can even have its own agent-like rules, right? So an individual square in the environment can take actions based upon what they see in the system, right? For instance, in some of the models, one of the models I'll show you at some point, we have grass in the system. We represent grass, and we have sheep who eat the grass, right? But the grass can become depleted, and the sheep have to wait for the grass to regrow, right? And so the environment itself can be an active agent in the system, if you think about it from that perspective. Time. Almost all agent-based models are time-based. Agent-based modeling is a model of process. It's a model of how something changes. It's not a model of pattern. It produces patterns, right? But it does not tell you what those patterns are or describe those patterns in any particular way. It's almost always a necessary example. There are some exceptions. For instance, I have seen people use agent-based models to solve complex equilibrium problems, right? In other words, what they're doing, if you think about game theory, think about the way the Nash equilibrium comes about. The Nash equilibrium comes about because a single agent in the system considers all the possible things that it could do and what its competitor might do in response to that, and then picks the one that's going to maximize its outcome regardless of what action its competitor takes, right? Well, what if we're in a world in which it's impossible to enumerate all those possible actions, but I can simulate them, right? So then I can have an agent who simulates a whole bunch of future possible actions and then determines what action it's going to take based upon all those simulated results, right? And in this case, there isn't really a notion of time. We're just talking about what the next action the agent is going to take is. But there is kind of a notion of time because in order to run all those simulations, I'm essentially simulating the time forward from the point of that particular action that the agent took. Adaptation. Adaptation is when agent's actions are contingent upon its history. The brief way to describe this is that if given an agent state, it takes a different action in the future based upon its past actions, right, then that agent is adaptive, right? So if I walk into the party and it's the same 20 people, and I use a different rule of behavior to decide who to talk to this time than I did the last time because I didn't like the way my last rule worked, right? Then I have become an adaptive agent. If I always use the same rule of behavior, I am not an adaptive agent, right, in that particular context. As I mentioned, I don't know of any other modeling approaches that really allow you to do adaptive agents in your system. So a lot of times we'll talk about the difference between agent-based models and equation-based models. An agent-based model, because the computational model, has a different representation than an equation-based model where you're writing out set equations. I often show my models and people ask, well, where's the math? And I'm like, well, there is no math, right? There's computational processing, right? There is a mathematical equivalent. We know that because there's something called the Turing completeness theorem that says that all these systems are actually equivalent to each other. But the representations are so dramatically different that I can't call what I have a math, right? It's computer. It's computational processing. It's different than math, right? Many equation-based models make the assumption of homogeneity. Now, by the way, this list is controversial because people will say, well, I know of an equation-based model that doesn't make the assumption of homogeneity, right? Or I know of an agent-based model or an equation-based model that doesn't require aggregate knowledge that loads local knowledge. These are all true, right? You can do equation-based models that violate these assumptions, right? But in general, you get to a point eventually where it's like, well, if you're violating all those assumptions, why not use an agent-based model? Because the equation-based model is not gaining you anything anymore, right? The whole point of an equation-based model is that when you make all these assumptions, you can prove things nicely about the system, right? But if you're doing an agent-based model, if you're doing an equation-based model and you break all these assumptions, you can't really prove that much anyway, so why not just use a simulation at that point? So many equation-based models make the assumption of homogeneity. They're often continuous and not discrete. This results in something known sometimes as the nano-WOOF problem. So if you're using there's something called the Locke-Volterra equations that talk about population ecology and how predator-prey species interact. And if you think about it, if you have a bunch of wolves and you have a bunch of sheep and the wolves eat the sheep, right? Eventually, if the wolves eat too many sheep, they can't find any more sheep to eat, and they're going to die off, right? But it doesn't actually, in the Locke-Volterra equations, there's no notion of an individual. There's only notion of the number of wolves there are. And so if there's half a wolf, that half a wolf can still reproduce to cause more wolves in the equation-based model, right? There's nothing to stop a millionth of a wolf, the nano-wolf, from coming back to 1,000 wolf population. But in reality, we know that when you get to less than one breeding pair, the population has gone extinct, right? Now, you can do discrete equations. There are discrete equation-based models, right, that will allow you to represent that appropriately. But a lot of these systems, when they prove these nice limits about them, are done using continuous modeling, right, which suffers from the nano-WOOF problem, right? That you can have these cases. A lot of equation-based models require aggregate knowledge, right? Like, I need to know what the population looks like before I can write a set of equations describing the population. In agent-based models, we can do things like look at individual rules and just aggregate to the aggregate level, right? Now, it's hard to validate that our aggregate level is right if we don't have the aggregate knowledge, but we can start to think about what might happen. Ned Smith and I did this in a paper that we just published in Management Science, where we talked about how people decide to get a job or not, what job they should get or not, right? And we didn't really have a lot of aggregate data, but we did have data from lab experiments where we talked to people and asked them how they decide what kind of job to take. And we simulated those patterns of behavior, and we showed that general patterns that we observe in the real world, like bimodal distributions of wealth, would arise from these kind of individual level rules, right? The ontology of equation-based models is at a global level. What I mean by that is equation-based models say that there is a population of the employed or the unemployed. It doesn't say that this individual is employed or unemployed, right? And so as a result, it's harder to draw that level, that connection to the real world system as much. There's no local detail. If I know from an equation-based model that I've created that 1,000 people will be unemployed next month, right? I don't know who those 1,000 people are, and I don't know where they are usually, right? Whereas the agent-based model would be able to make predictions of exactly which individuals are likely to become unemployed. Equation-based models are generally top-down. They think about the system at a whole level, right? Whereas agent-based models are bottom-up. They think about how the individuals give rise to behavior. Equation-based models are generalizable, right? So if I write down a set of equations and I say that, write down the assumptions under which those equations are written, right? Then theoretically, I can make proofs about those equations that hold true for as long as those assumptions are true, right? I can't do that with an agent-based model, right? An agent-based model, all I can say is that for all the conditions I've tested, this result holds true. But there might be some conditions I didn't test for which that result doesn't hold true, right? And so it can be built up and it can complement these equation-based models, but it doesn't have the same generalizability. Agent-based models also have a relationship to statistical modeling, right? So the problem with statistical modeling is it's hard to link statistical models to first principles in behavior, right? How do I go from an aggregate knowledge of market sales to why an individual decided to make a particular purchase? I can't do that very easily using a statistical model. Agent-based modeling can complement that, though, by saying if people are making decisions in this way, these are the statistics of pattern buying that I'm likely to see, right? Buying patterns I'm likely to see. Right? So that can be natural complements. Lab experiments. So agent-based models can complement lab experiments, right? And this is exactly what Ned and I did, right? Lab experiments generate theory about the way people might behave, but they're rarely scaled up, right? People don't often, do a lab experiment on 20 undergraduate psychology students and then say, oh, what will happen if 1 million people were to operate on that? They don't have a good way to test that, right? An agent-based model can provide us with that tool. We can say, well, if everyone operates the same way those 20 undergraduate psychology students did, who are probably not representative of the whole population, right? This is what would happen in the whole population, right? And we can then say, well, then it is representative or it isn't representative or it doesn't really work. We can also generate new hypotheses. So let's say we run our lab experiment, we build a model, an agent-based model from our lab experiment, and our agent-based model produces interesting results that don't seem easily explained by our lab experiment, right? Well, then we can go back and say, well, let's start a new lab experiment to test those new results that we just got, right? We can use agent-based modeling to determine the sensitivity of the results, right? People in lab experiments can only be forced through so many conditions before we suffer from experiment fatigue, right? They don't want to pay attention anymore. So we can run the model outside of those conditions and see if there's any unique results, and then we can go back and test them in the lab, right? And we can compare to generative principles of how these things might actually happen. So there's another type of simulation that's not agent-based modeling, but does happen in a computer, which I'll call aggregate computer modeling, right? The most classic example of this is something known as systems dynamics modeling, right? And system dynamics modeling was really popularized by John Sterman and some others at MIT, right? To try and write down complex systems as a series of equations that describe the interactions between what we'll call stocks and flows. Stocks are repositories of something, and flows are when those stocks transition to something else. And system dynamics modeling is great because it embraces the system-level view of the world. Agent-based modeling also embraces, right? It says that the results, the patterns of the world that we see are not the result of any one general system, they're the result of many components resulting in that overall system. But system dynamics modeling often requires you to essentially have an aggregate knowledge of how things transition, right? So rather than writing down that one sheep is eaten by one wolf, you write down that the population of the sheep is depleted at a rate related to the population of wolves, right? And so you need to have that knowledge of how those things relate. And if you don't have that knowledge, it becomes hard to generate these systems. Interestingly enough, again, these are good complements. You can use agent-based modeling with system dynamics modeling together. So what are the limits of agent-based modeling? We've talked a lot about now when you use agent-based modeling and how they might complement other things. But what are the limits? Well, first of all, it's a high computational cost, right? Agent-based models, you have to run a lot longer, right? Like if I have a game theory model, there's no running of the model, right? I have the model, it's there, it's done. Maybe I have to do some numerical simulations to kind of prove a particular result, but it's very minimal. Every time I want to build an agent-based model and get a result, I have to run a computer simulation, right? And some of these computer simulations can take, hours, days to even run, right? And so evaluating the different models can be very computationally costly. Agent-based models have a lot of free parameters, right? So we've had a lot of questions. Can you do this in agent-based? Can you do that? Yeah, you can do all of that, right? But every time you do something new, you're adding a new parameter, you're adding a new element to the system, which means you need to test and validate to make sure that that parameter is actually set accordingly the way you want it to do it, right? Now, I would argue that a lot of equation-based models have those same number of parameters, but they hide them from you, right? So they basically will say early on in the system, we're assuming that C is greater than 0, we're assuming this and this and this. And really, so those are all parameters, but they don't actually show up in the equation, right? Because of the fact that they're part of the assumptions of the system. Right? Agent-based modeling makes those parameters obvious. Agent-based modeling, it's very, very hard to write an agent-based modeling where you don't know how an agent behaves, right? So if you don't have any individual level knowledge, or at least hypotheses about individual level knowledge, then it's difficult to do an agent-based model, right? But I would argue that often provides you better insight into the overall system. So in many cases, these limitations are worth it. Why is there resistance to agent-based modeling? A lot of people have discussed this with me. I think that a lot of it has to do with lack of education about complex systems. People don't understand how these complex systems work. They assume that all the things they see are linear, right? There's a lot of what we call the deterministic centralized mindset, which means that people assume that the world operates in a deterministic way. Something happened. There must be a cause for it, right? Rather than the fact that random chance can exist in these systems. They assume that there's leaders when there aren't leaders, right? When you show the bird flocking model to people, a lot of people say, well, but yeah, there's someone in the front who's actually causing the birds to flock in different ways, right? People want there to be a leader. They want there to be a reason why something happens, and there's not. So that causes a lot of resistance. I would argue that a lot of people resist agent-based modeling due to this old parable about the drunk, the keys, and the street light, right? So the argument goes like, the story goes like this. Police officer is out walking and he sees a guy who's drunk looking at the ground around the street light, and he asks him, "Oh, what are you looking for?" He's like, "I'm looking for my keys for my house." And he's like, "Oh, well, let me help you." And he starts looking. He's like, "Are you sure he dropped them around here?" He's like, "No, I actually dropped them back there, but I can't see there because there's no street light. So I'm looking here where the street light is," right? And I think a lot of times people have that same attitude towards science, right? They see a particular problem and they say, "I don't want to use agent-based modeling because I can't, because I don't know how to use it, right? I don't have the light to use it that I need. So I'm going to use another approach that doesn't actually solve your problem, right? But I'm going to use it because it's the one I know about, right? And so I think there's a lot of that lack of education prevents people from adopting it a lot of times. So there's a ton of ways to use agent-based modeling as well, besides the standard approaches that we've talked about. Like, you can think of models, and this is true of many models, but it's particularly true of agent-based modeling. You can use agent-based modeling as a description of a system, right? So when I build my segregation model, right, I'm not really trying to predict how segregated a neighborhood is going to be. I'm trying to describe the patterns of behavior and better understand what's happening within the system, right? Models that are not simplified are useless, right? And as this quote from Albert Einstein is actually not quite correct. I've realized since I put this up on the slide. He never said this line just in that way. He said it in a more complex way. But basically it boils down to make your models as simple as possible, but no simpler, right? And that was his goal. Explanation. An agent-based model provides explanation of potential underlying phenomena that control a system. They are a proof of concept, right? So you can have a theory that this is the way the world works, and if you run your agent-based model based upon that theory, and you don't get the patterns of behavior that exist in the real world, that probably says that there's something wrong with your theory, right? If you do get the patterns of behavior, it doesn't necessarily say that you're exactly right, but it's at least proof that that's at least potentially one way that the real world system could have happened, right? So, sometimes we call them, another word that John Howland liked to use was intuition pumps, right? I run my model, it gets results that are close to the real world. That helps me think a little bit better about other experiments I might run, other tests I might run, to see if that's really the real world, the way the real world works. Experimentation. I can run the models many, many, many times. I can experiment with the results, and I can see what the results of those are, and look at those results and compare them to the real world and tell their phenomenon, right? Analogy, right? So the Boy's model, even when I showed it, we already started asking questions about, does this tell us anything about human behavior, right? And that's exactly the point of a lot of agent-based models. It's not to necessarily tell us about how the birds act, but also how other things that act in similar ways might behave, right? And like, the model of flocking birds, as I mentioned before, was actually used to understand locusts, but it's been also used to understand fish, right? So we can analogically reason from one model to other models. Another kind of interesting example is that they've also been used to help engineer systems. So I can use the Boyd's model to understand how birds flock, and then I can think about, well, what if I built those rules into a flock of drones, right? Would that be useful, right? And so I can analogically reason from birds to drones, right? Another model that we haven't talked about yet, but there's a model called the ant colony model that talks about how ants find food. And that model actually was used to design something called the ant colony optimization algorithm, which is actually one of the fastest ways to route network traffic over a complex network, and like the internet traffic, right, over a complex network. Because it's not always clear what the best path is between any two nodes on the internet, right? And the ant colony optimization algorithm has been shown to be one of the quickest ways to route that, right? Essentially using pheromones on the internet to track things. Agent-based models can be used for education and communication, right? In fact, NetLogo is by far the most widely used agent-based modeling platform in existence, not because of its use by scientific researchers, but because of its use at the K through 12 educational level in the United States. A lot of school systems are using NetLogo not because they want their kids to write computer code, because they use the models to teach phenomenon, right? Like they use it to teach things like traffic patterns, or, in fact, if you look at the NetLogo models library, there's models of like physics and electronics and all these other different systems out there that are actually used in real world classrooms. Touchstone. I think of agent-based models as something we can all get behind, right? So like essentially, if we have two competing theories about the way the world works, I can write an agent-based model that describes my theory, and you can write an agent-based model that describes your theory, and we can compare and contrast those models, right? they allow us to move beyond words to concrete objects, right? They actually talk about the way that system works, right? Seymour Papert called them objects to think with, right? They're physical objects that allow you to still express your thoughts, right? They give us a complex common language to describe these phenomenon, and they allow us to change a complex system into a specific set of rules. Agent-based models can be what sometimes referred to as Gedanken experiments, the German thought experiments, right? They allow us to say, well, what if the world worked like this, right? What if this was the patterns of interaction, what would result, right? And so we can explore things that may not even exist in the real world, and we can look at that through a few basic, simple rules. Finally, and predictions, right? A lot of times we talk about predictions from models, but and this came up. Someone asked about the Osama bin Laden and Hurricane Sandy pictures, right? So you're saying that you can use those to predict future conversations around those topics, and I'm like, yeah, it's a difficult question, right? Like the future is almost always different than the past, right? So things are going to change, right? But hopefully, if we can build a model that best understands how humans interact, how humans talk to each other, right? Eventually, we'll be able to get some predictive power of how conversations in the future will go, right? And it's hard. It's difficult. It's very hard to do. But any modeling approach is hard to do, right? Anytime we build a model, we're making the assumption that the past is going to be representative of the future, when in fact we know that that's not the case, right? That things are going to change, right? It's one of the reasons why I think the social sciences is really the hard sciences, right? And this is the way it's been used, because human behavior is much, much less predictable than the behavior of a couple of atoms, right? Or even a couple of birds, right? And so trying to understand these systems and make accurate predictions is very difficult. So yes, agent-based models can be used to think about future scenarios in the future world, right? But the validity of a prediction is determined by how well the model has been validated. And it's difficult to assess the validity of any model for an event that has never occurred before, right? There's this Heraclitus quote that, man never steps in the same river twice, right? And the reason why is because even if it's the same river, it's been changed by time since the last time you were there, right? So even if I have the system that is almost exactly the same as it was 10 years ago arise, right? Let's say another hurricane that's just like Hurricane Sandy hits the East Coast, right? Well, dynamics have changed, right? Maybe there's more people on Twitter. Maybe there's less people on Twitter. Maybe people are using Twitter in a different way, right? Maybe there's new news channels that spread information in different contexts, right, than they did 10 years ago, right? And so, yes, I can never make perfect predictions, but hopefully we get to more and more generalizable models, more and more interesting models. We tend to get a better understanding of the world, right? Eventually, I'd love to see agent-based modeling take the role of something like this idea that Isaac Asimov presented called psychohistory, right? So Isaac Asimov has a series of books called the Foundation series, where he talks about a secretive group called the Foundation that tries to foretell where the masses of humanity are going, right? How they're going to change, how they're going to alter in terms of society and the way the world is, and then tries to prevent disasters from happening, right? Essentially is what the goal of the Foundation is, right? And they do this based upon a science of psychohistory, which in the book is described as a combination of history, sociology, and mathematics to make approximate predictions about the future behaviors of large groups of people, right? And one of the hopes of complex systems and agent-based modeling, right, is that it has the potential to understand how large groups of individuals and organizations will react to future events. I would argue potentially paving the way for a real psychohistory, right? However, as I said, in both cases, the goal is not to make a specific prediction. The Foundation never tried to make like a prediction that the total number of bananas grown in India next month will be X number, right? They're just trying to understand how those numbers are going to relate to other numbers and whether that puts humanity on a good course or a bad course and how you might change things to affect them in that way. And for me, in terms of the applications of agent-based models to economics and social sciences, that's really the goal, right? Let's understand the world. Let's try and figure out how we can intervene in that world to make it a better place, right? And let's try and describe how we might do that. So with that, I think I'll end for today, for lunch at least, right? And we can take the lunch break. And then when we come back, we'll start playing around with some of these models. So thanks, everybody. 2:30, sorry.